Hello again, it's Miss Sarika with part 2 of the notes. So in the first part of the video key, we talked about how Earth's layers are formed through planetary differentiation, and that these layers are specific based on their densities, most dense to least dense, and that we've got all this different energy moving and all this matter moving inside of the Earth. So now how do we even know this? How do scientists know this? So the next question in the notes is, how do waves tell us what inside of Earth is like? Because we can't just like slice the Earth in half and take a look at it. That would be, really easy, but we can't do that. So what evidence do we have? The first is about waves refracting. And if you remember, this means that waves are bending their paths as they go through a different substance. So each layer has a different density. As the wave hits that layer, it bends and changes its path depending on the density. And, even within the layer, there's some variation and variability within the density. So it can bend. So how do we know this? Well, we get the different measurements of time for how long an earthquake takes to get somewhere. Because, if the earthquake occurs here, we would expect if everything was the same inside of Earth, it would just be like this, and all the earthquake waves would travel in a nice straight line, and we could measure the time on our little seismographs, and we can measure the intensity, but it doesn't happen that way. So we know that we have some expectation of how they should hit these different points on Earth, but they don't match up with, an image of if this is the earthquake, that the waves just go straight. So we have different times, we have different speeds that they travel, and therefore we can put together this picture like down here, where the waves bend. So it's kind of complicated that you don't really need to know exactly how at this stage, just know that the waves do bend. And you'll see that they have this kind of curved path, depending on if it's an S wave or a P wave. Now, we'll get to why there are no S waves in this outer core in just a second. So the next, I gotta move again. Okay, so if we look over here, you can see waves reflecting. That's the next piece of evidence. So what does that mean? Reflection. Think about looking in a mirror and your image reflects back at you. So reflection is when waves bounce back when they hit the different substances of different layers. So how do we know this? They bounce back and we can record that. So we can, create our own actually, aside from just seismographs, aside from just seismic energy, scientists actually can send that sound wave down to get that information too. So what it looks like is that they hit the they hit the layer and it bounces off. All right, the next piece of evidence is that S waves don't travel inside of the outer core. Well, what does that mean? S waves cannot travel through the liquid of the outer core. So they can't travel through liquid at all. So the outer core must be a liquid. So there's a kind of complicated explanation to that. The idea is that these are transverse waves, side to side. And when they hit that liquid, it doesn't snap back as easily. And so it kind of just dissipates the wave. So it doesn't have the ability to travel through the liquid material. So we get these shadow zones, and these shadow zones would be like kind of down here where you would expect, the wave to continue, but nothing occurs there at the stations that would be recording seismic data. So that tells us that the waves are getting stopped somewhere, and it ends up being that there's liquid around this solid core of the inner core. All right, now let's go back over here. Whoops. All right, so why is speed different through the layers? So waves change speed through the layers of Earth. So we have lots of evidence for this based on how we, get data at different points around the Earth. So why does it do it? It has to do with density. So things that are more dense, less dense, more dense, less dense. So when they are more dense, the waves can send their energy through the particles a lot quicker than when the particles and the atoms of that medium or the layer's rock material, it can't travel as fast when it's farther apart. So the waves go a lot faster. So here's a graph that you need to be familiar with. Wink, no nudge. So make sure you're familiar with this. If you look, we saw this before already. There's wave velocity, depth, and then layers are listed over here. We've got S and P waves. So let's just look at this S wave. As we trace this and we go deeper and deeper, we're going to see something happening to the S wave. Same thing's going to happen similarly to the P wave. So what is actually happening? So I've got a couple different things. Let's start with the P wave. So the P wave, generally the speed is increasing. It gets faster and faster and faster the deeper it gets. But what happens is they slow down at the outer core. So this line here is a boundary line between the mantle and the outer core. And it dramatically decreases its speed at this point. Well, why? Well, now this is kind of weird because the outer core actually is more dense than the mantle. This is where that funny stuff with the liquid happens and how the waves kind of impact traveling of the S waves. Well, it does impact the P waves as well. So in general, just understand that there's something happening here with the material. This one's not necessarily due to density. It's a little funny, but just know that it's changing its layer right there. And you'll notice that, at all of these layer lines, because there's some variations in the mantle, that at all of these layer lines there are jumps in speed, and that indicates that we've changed to a new layer. Just look here between the outer core and the inner core when it jumps up in speed. So a good way to know that it's changed to a different material with different density is to see in this speed graph that it has like a little jump or a little hop. And whether it's going faster or slower, it doesn't matter. It's just that little jump indicates that there's a change in density and a change in the layer. So the S wave is very similar, except that it stops. So when it hits the outer core, it will slow down or stop. So in general, it'll slow down or stop in a material that's less dense, but specifically because the outer core is made of liquid material, that's definitely going to impact how the waves travel. All right, so big ideas from this, that there are 4 main ideas that you need to know of the evidence that we have for what's going on inside of the Earth. The first is that waves refract, or they bend. The second is that waves reflect, or they bounce. The third is that there are no S waves in the outer core. And the last piece is that waves travel differently through different densities, and they will go faster in more dense material and slower in less dense material. So we get all these images and we get all this data, and there's a lot of more complicated kind of physics behind this, but we get the kind of the basics here. When you put that all together, we kind of understand what the different layers are and their densities based on some of these factors with how the waves travel. So the interesting thing is that all these earthquakes happening give us a lot of information that tell us what's going on inside of the Earth, because they're really the only things that can travel through the entire Earth. So there you go. There you have it. Enjoy, and if you have any questions, come find me.